Thanks, Ben. Good afternoon, ladies and gentlemen. I hope you made good use of the break to relax a little bit. You will need it. There are lots of slides. As Ben mentioned, we're going to talk in this session about compact device modeling for RF circuit design, which means high-frequency applications. Oops. We're not moving that fast. Here's an outline of the talk. I'll have an introduction just to give you a little bit of motivation of why we do compact modeling. And then I go through models for active devices such as bipolar and MOS transistors. Before we go to passive devices, we have to talk about parasitics and parasitic effects. We already had these things mentioned as important in the previous talks. Then talk about passive devices here, and then I have a small section on RF device modeling issues and also a few slides on model verification and validation. So if we talk or think about applications that focus on high-frequency operation, then we usually think of communications. But from a modeling point of view, in general, we have to cover many more applications, such as those that are listed here with, for instance, extreme frequency ranges or fairly high voltages. People don't want to use a different compact model for different applications. They don't want to learn new models for various applications. Also, when we formulate models, we have to cover a large variety of process technologies, as you can see here in that little list. And finally, circuit design today is CAD and simulation based. So we really need what we call compact models, and let me define that to get everybody in the same boat here. Let me define that briefly. A compact model, as we understand it, is a representation of the distributed regions which we have in every device by lumped elements, as you can see here in this little equivalent circuit, with describing these lumped elements with sufficiently simple equations. And I'm going to talk about numerical tools as well, which are not suitable for this. And we try to achieve also an as simple as possible equivalent circuit, because if it is too complicated, it just takes too much time, and designers will complain. What do we have to cover in terms of devices? The left-hand box shows what we see in typical BiCMOS process offerings. We have active devices such as bipolar transistors and MOSFETs. We have a whole bunch of passive devices, and they all come in different flavors, which could be different geometries or different doping profiles. And then there is the unavoidable, which are the parasitic effects. I've listed a couple of them, and we will talk about them. And there's nothing you can do. All these devices will have parasitic effects, and they are becoming increasingly important for high-frequency operation. And what we need to do is we need models for designers that describe the operation of a device as a function of bias, frequency, temperature, geometry, and not to forget process tolerances. Well, sometimes, or actually fairly often, if you look at foundries or in the companies, you get statements like, all the models are wrong, our circuits don't work, and usually it gets blamed on the models. The question now, if you ask a designer, is, so how many circuits did you design without models? Then you usually get the answer, no, well, I always use models. So models are useful. The problem we have today is that nobody has time to look at the limitations, and from the modeling side, nobody has time to put the limitations into the files so that people can read it. So usually, if you design something, you have to know the limitations of the model. You can't design power amplifiers with a model that doesn't cover high current effects and saturation in the bipolar transistor. And that's a little bit the goal of this presentation, discuss some fundamental principles for compact modeling of RF devices. So people you should get an idea how models get constructed and what is important. This slide is admittedly fairly busy. I'm not going to read all these little sub-bullets, but what I want to show is, and I want to give you basically, first of all, the requirements for compact models that all have to be fulfilled simultaneously, and many of them are contradicting. And the point here is that we have requirements from circuit design, from process development communities, but also from modeling folks, usually in terms of parameter extraction, and from CAD companies when we want to implement a model. And it is very difficult to achieve all these requirements for a production compact model. There have to be compromises, and those compromises lead to validity range limitations in a transistor model or in any type of model. This is for a motivation, looking at basically mask cost for subsequent CMOS generations, and we are approaching $750,000 for a mask for next generation processes and going towards $1 million per mask. And that pretty clearly tells us that if you can save a cycle, a complete mask, by reducing design iterations and by applying good modeling techniques, we actually have paid for ourselves as modeling engineers. That's usually the budget of modeling groups in many companies. So just one design iteration already helps us. This is, what happened? This is so this is really thought as a motivational slide. Let's start with talk about bipolar transistor modeling. What you see on the right-hand side is a little bit an overview in terms of transit frequency in gigahertz versus year. The development is exponential. There's one company, or two companies actually moving ahead compared to the bunch of others, but it clearly shows that we're moving well above 100, 200 gigahertz in bipolar technology, and we have to cover the physical effects occurring in these processes. And when we talk about bipolar transistors, we usually think about applications in wireless or wireline circuit design, for instance, and as a consequence, model development is mostly driven by those communication applications. And that is in contrast to CMOS, which we will talk about in a couple of minutes. So, there's one problem we have in bipolar: there's no real process compatibility. And we have to cover many different process versions, hopefully and preferably by a single model. And the model usage still in many companies, especially in the MMIC gas area, is that there are just a few devices that get measured and parameters extracted on. And even in the Silicon IC design community, there are still a lot of companies that just provide you with a couple, let's say 5 to 10 transistor models, which is not suitable for circuit optimization. What I want to do in this talk is I want to focus on silicon-based technologies because there's really not enough time to cover many different technologies here. So if you look at bipolar transistor models, what's available? First of all, in contrast to MOS, there is just a very small number of transistor models available, and the classic solution is the well-known Spice-Gomer-Poon model that is a standard model since the 70s in the simulators. But the problem is that it's becoming increasingly inadequate for modern applications. And here's an example. You see the transit frequency again for a really, straight production process, about just a 25 gigahertz process, to show you that even 2 or 3 process generations before the time now, we had problems already with the Spice-Gomer-Poon model. You see the lowest curve, and you see some dashed curves here. The dashed curves belong to the Spice-Gomer-Poon model, the circles to measurements, and just the lowest curve can be fit with the Spice-Gomer-Poon model up to about FT peak. The other dashed curves are somewhere in between, and in more modern compact models, you can actually capture this behavior much more accurately. And similar problems exist for the Spice-Gomer-Poon model for other characteristics. Now, there are, as I said, few more models, and the solution that came out and was available in circuit simulators in the mid-90s, it was the VBIC model, and the most important contributions were to extend the Spice-Gomer-Poon model to quasi-saturation, introduce bias-dependent early voltages again, and also add a self-heating model. And that's already serving a lot of purposes in the design community. And then there are two more advanced solutions, which one of them is the Maxtorm model and one of them is the HiCom model. And if you're wondering about this dashed line here, it's just supposed to indicate which model is more suitable for which of these features that are listed here. Just down here, there's a bunch of features, and if something is more on the right-hand side, then this model is capturing it more. Something is more on the left-hand side. The other model is capturing it more just by design. Talking about bipolar processes, which you all have to capture with a single model, the previous talk already went through what we call a drift transistor in various designs, where we have a highly doped emitter, a moderately doped base, and a graded germanium profile. But there's one more type of technology, which I only know one company that fabricates it, actually in production. That is similar to gas HBTs, what we call a real HBT. And you can see here, if you draw a line underneath the emitter, the profile, it has a moderately doped emitter and a highly doped base and a box germanium profile. And you can imagine that looking at the cross sections, that the structural differences force some differences in the scaling equations on the one hand, but also the differences in the vertical profile lead to some different effects in these transistors, and we have to cover them all and capture them in transistor models. This is a close-up of the, first of all here, of half of the emitter base region underneath the emitter and at the perimeter. And I've inserted into that cross-section typical elements that we need for constructing a bipolar transistor model from a physics-based point of view. So we see the transfer current source. Here we see the diodes covering the injection plus depletion capacitances plus possible diffusion capacitance that are all represented by these filled symbols. Then there could be a breakdown source. There's a base resistance and elements also for the perimeter portion of the transistor. And the right-hand side shows the external portion of the transistor, which contains all the unavoidable parasitics. For instance, spacer capacitances, distributed base resistance, parasitic base collector capacitance, a substrate with a typical simple substrate network and a capacitance, etc. For not too high frequencies, we can lump many of these elements and come up with something that looks a little bit simpler but still pretty busy, and this is a typical equivalent circuit for the modern bipolar transistors, be it VBIC, Maxtorm, or HiCom. It's a pretty typical equivalent circuit, pretty busy and pretty difficult to understand for designers. We know that. There is, in addition to the elements we had before, there is a self-heating thermal network down here, and the right-hand side just lists many of the features that we have in those models typically. The next two slides I'm going to go through very quickly because of the lack of time. The important point I would like to make here is, I know that they're busy, but they very concisely describe one of the fundamental equations we have in bipolar transistors. We have this equation in every bipolar transistor model. It's a single piece, continuously differentiable equation for the whole operating region. It's not like MOS where you have to piece things together. And it basically has a transfer current as a function of the applied voltages and contains also a stored hole charge. And the important point is that you can take into account different types or forms of the germanium profile plus the usual doping profile differences. And you can explain why early voltages are higher in silicon germanium HBTs when they have a graded profile, etc. And the next slide just shows the meaning of many of the charges that occur here. But as I said, there's more details that would just take too much time. So I'm going to skip over these and come to an important element and component, which is the base resistance in a bipolar transistor. What you see here is a single base transistor, and we have pulled out a plane here underneath the surface through the base and plotted the current flow lines and the equipotential lines. And as you can see, this is the emitter here, and the base current that is flowing from the contact will come out of the surface. And you can see that there is a very non-symmetric current flow. There's much more current flowing, just by counting the lines, flowing into the front side compared to the back side. And that is a a highly three-dimensional effect, and that has to be captured and covered, and actually is covered by very compact equations for modeling the base resistance as a function of emitter length and width and aspect ratios, basically, as a function of the contact configurations. There can be many different contact configurations in the bipolar transistor, and as I said, there are accurate equations to do this. And I want to conclude the section on bipolar transistors with a little summary here and just focus on 2 points. One of them is power amplifiers. We have advanced bipolar transistor models, but we still have to piece them together properly and add features in order to be able to capture or model power amplifiers and design power amplifiers really on a computer and not do this experimentally, as this is being done very often in practice. And the other thing I like to mention is that we have such a large variety of technologies that geometry scaling is, which we need for statistical modeling and other things as well, is very difficult to include in the model equations in a circuit simulator for reasons I'm going to mention later on. And you're better off in having this as a separate thing where you can focus on bias-dependent equations and geometry scalable equations in different tools. Let's move on to MOS transistor modeling. Again, on the right-hand side, there is a little overview. We already have seen FTs versus, for instance, in this case, current density for various MOS generations, and most of you know that the performance of the device is good enough, for instance, to start designing circuits above a gigahertz in CMOS. And I've listed a couple of applications here where MOS is being applied to, but there are a bunch of design issues listed here, and one of them is to obtain suitable compact models to design MOS circuits. And that causes one of the bottlenecks in RF CMOS circuit design. If you look at MOS compact transistor models, then first of all, we will notice, if you look at a simulator like HSpice, you will notice that there are tons of MOS transistor models available, and there's really the question, which one to choose. The problem with these is that the development of most of these models is driven by digital CMOS, and many of the features, they're lacking many of the features, the models lacking many of the features that you need for analog design, and they become unsuitable for high-frequency modeling. If you take a look at the most well-known models, and just to give you a rough overview, we can divide the model development effort into models that are threshold voltage-based, models that are surface potential-based, and models what I would call design-based, analog design-based. And there's just one model which I know where people really have come from analog design, GM over ID approach. The others are trying to more coming from the physics-based approach. And if I say, for instance, surface potential-based, the meaning is that people try to model the surface potential of a MOS transistor as a function of bias, which is not, and as a single piece function, which is not an easy task. Looking at, for instance, geometry scaling in a MOS transistor and extending a MOS transistor model, an existing model, to a high-frequency model, first of all, we're faced with the task that geometry scaling usually in simulators doesn't work properly, because we have to model a structure that has an interdigitated source gate drain configuration. In this case, for instance, we have a drain, we have the gates connected at two sides in order to lower the gate resistance. We'll talk about this. And we have to extend the geometry scaling equations of typical existing models properly in order to incorporate a bunch of effects. For instance, one of them is shown here, where we have at high frequencies strong coupling between sources and drains just through the substrate, and also coupling to the bulk, of course. This is a close-up again, including physical elements of an equivalent circuit. The MOS transistor basically the MOS transistor operation sits here, and all these elements you see are additional elements that we very often don't find in compact models. For instance, there's in this case a resistive network for substrate coupling, there are contact resistances, there's an overlap capacitance, and there is the series gate resistance and even a series gate inductance, a self-inductance. And we can lump at not too high frequencies these elements together and come up with an equivalent circuit shown here, a compact equivalent circuit where MI is any analog suitable MOS model that you can find that captures the intrinsic device operation reasonably well. And then we have to group all these elements, other elements around it, including even possibly inductances also for source and drain that are not inserted here. This list just summarizes what I just said about the various elements in a MOS transistor, and I have a couple of those lists following the cross sections. They just don't fit on one slide. So I'm going to skip mostly those lists. It's just a summary of what I said before when I explained the equivalent circuit. Now let's talk about the gate resistance in MOS transistors. In the previous talk, we heard this factor 1/3, how a distributed gate resistance has to be modeled. And what you see here is if you feed a signal from that side into the gate, this is the width of the device, you basically see at not too high frequencies, first of all, an RC line. This is a distributed RC line, and this problem can be solved analytically in closed form. It gives an infinite series, and that was actually done in the 50s for a similar, basically for a bipolar transistor, but you can apply those things right away to MOS transistors. It was reinvented, I think, a couple of years ago, the result of it is that after terminating the series, the infinite series after the first term, you get a gate resistance that is shown here that contains the factor 1/3 to take into account the distributed nature of the current flow. Part of the current just flows down, part of the current keeps going here. And also, to model the shunt of these capacitances at high frequencies, a parallel capacitance can be added that represents the first order solution of this network here. And this is a compact representation of current, basically high frequency current crowding in a gate. I would like to mention one thing is, if you're looking at shrinking device dimensions and compare MOS and bipolar transistors, then you will find that shrinking dimensions in gate length direction will increase the gate resistance, and if you apply the same lithography to a bipolar transistor, it will decrease the base resistance in a bipolar transistor. So they are opposite trends, and there will be more and more emphasis to be put on the gate resistance in MOS transistors. Let's talk about parasitic effects, which are common to all devices. I would like to talk about substrate coupling, electrothermal effects, a little bit about lines at high frequencies, and metalization capacitances and inductances we have in the devices. And what we want to have is a compact and physics-based representation of all these effects for design and synthesis of circuits. Substrate coupling, something I would like to explain based on this little figure here. Let's say we have a chip and a large CMOS part, and then some back-end circuits and devices here, or front-end, whatever you want to call it. We will have a lot of noise, switching noise, coupling into the devices here that are the dashed lines, and also between the front-end devices there will be a signal path through the substrate. That is called inter-device coupling, and on top of that, the solid lines show the intra-device coupling, where we have, for instance, a buried layer here at high frequencies talking to the substrate contact wherever it is in that device. That is called, as I said, intra-device coupling. There are two different things, although the modeling methods can be similar. The existing work is mostly focused, let's say, on digital CMOS circuits, mostly resistive couplings up to a couple of gigahertz. There is very little on frequencies much higher than 5 gigahertz. For instance, frequencies up to 40 gigahertz in fiber optic systems. And the practical issues here is that there's two things. One is that the coupling impedances here in the network representation is unknown until we know the layout of the circuit. So if you expect from your modeling folks to give you a model that contains the elements, then you will be disappointed because they can't give you any compact model for the devices, for instance, until they know the layout. So this is sort of a back-end extraction issue, especially for inter-device substrate coupling. The other point is that the coupling itself is usually a very complicated three-dimensional problem. It's not as easy as it looks in the first place. This is, it is really difficult to calculate analytical equations, compact analytical equations as a function of geometry. And there are, in fact, no general solutions right now available that we can apply to compact modeling. Let's step back and see what we can do in order to model this. Of course, I mean, we can solve Maxwell equations, but this is overkill. It's computational overkill and is also not necessary. We can simplify the equations to the semiconductor equations typically found in device simulators. That works well, is much faster, but we can even combine Poisson's and continuity equation to a single equation that can be solved fairly quickly for three-dimensional structures, and that is sufficient for the substrate coupling effects and describe them as a function of geometry. If we reduce that equation to a Laplace equation, we can get either capacitive or purely resistive networks. In some cases that may work, but for high frequency, let's say fiber optic circuits, you would prefer to do this and solve this equation. The other thing is, when do we have to consider more complicated substrate coupling networks and start to consider, let's say, the silicon's permittivity? You can estimate that fairly easily by calculating the corner frequency of the substrate that basically is given by the substrate resistivity and permittivity. And there's a numerical example here for 15 ohm centimeter substrate. The corner frequency is about 11 gigahertz. This means that you have to include the permittivity of the silicon substrate at this frequency and possibly even a little bit lower in order to take into account the capacitive coupling on top of the resistive coupling. As I said, in compact modeling, we don't have a compact analytical form, but so what people usually do is they solve the numerical, with some numerical simulator, they solve the problem numerically and then fit a given set of equivalent circuits to those numerical solutions. And of course, that tells you that this approach is not very flexible because it takes time to generate those solutions. It's not very flexible if a designer wants to change the layout. This figure shows the impact of substrate coupling, again, on a simple 25 gigahertz production process. It basically tells you that we already had these problems 5 years ago. The circles here, this shows the real part of the output conductance versus frequency. The circles are measurements. The dashed line is a compact model without substrate coupling network. And if we add a substrate coupling network across these lines, here along these lines, then we get a very accurate description of the coupling and the output conductance. And the difference, if you look at 2 gigahertz application, the difference is about a factor of 4 in the output conductance. So it is significant. And mostly talked about the inter-device coupling already at the first transparency. And this is just a summary of what I said. And the last point is important to mention again. You have to fix the substrate contacts for devices, for instance, and for chips. If you're designing circuits, you have to add an extraction program similar to the backend extractor that gives you all the substrate elements. You can't expect from the modeling folks to give you that before the layout is known. It's very important, but it seems to be difficult for some foundries to accept this. The next parasitic effect we find very often in modern technologies is self-heating, or in this case, we just call them electrothermal effects. Let's look at this figure here. This little volume here is a heat generation source. So there's a power generated by the current flowing through the device and the voltage across the device. And the arrows indicate where the power is flowing or the heat is flowing. And most of it is going down to the substrate. Part of it is going to the next finger, heating the finger up. Part of it is going to the next device, which would be then inter-device thermal coupling. And there are a couple other paths where the heat can dissipate. If we look at existing work, we will see that in the 3.5 area, the gas guys, as we usually say in the package engineering, they have a long history of dealing with these problems. So we just have to go across, look at across the wall and adapt some of the things that they already have. The practical issues here again are that the coupling impedances can only be determined after the layout is known. Same thing as a substrate, and it might have struck you immediately that this is a very similar problem as the substrate coupling problem, and in fact it is. And usually this is again a very complicated three-dimensional geometry problem. What is the basic, are the basic methods to solve this problem? Of course, starting with the heat equation is a good idea. The heat equation is a nonlinear equation because of the temperature-dependent thermal conductance. The other variables are listed here that occur in that equation here. People usually perform a Kirchhoff transformation to make the equation linear. Actually, it is only quasi-linear. And if you transform the time as well, then you can come up with a linear differential equation that you can solve analytically for not too complicated problems. And that is being done. There is a bunch of solution methods here, from numerical solutions, computationally just too expensive for circuit design, to analytical, fast analytical solution. And this is a very good reference, is a very long paper as well, from the gallium arsenide area, where people have provided a very nice solution to this problem, or how it could be solved in practice. Looking at compact models, the question is, how do we realize a solution of the heat equation in a compact model? And what we do usually is we construct a lumped element representation with an infinite number of R's and C's, or a finite but large number of R's and C's, driven by the power source, which is a current source here. And the result is the difference in the temperature. So it's an additional temperature to the device temperature. Then we feed the temperature back to the compact model in a simulator, calculate all the temperature-dependent model parameters, and do the iteration again. Actually, in practice, we don't use such a sophisticated equivalent circuit, although it only has 2 nodes, but there's a lot of parameter extraction involved. People have difficulties to extract all these elements. What is being done in most practical compact models is to use a single pole thermal network. We have the power source here again, we have this temperature difference, and we do the same thing as we would do with an infinite number of elements. If we want to take into account thermal coupling, we need to make this node here available to the external user. In most simulators, it is not available, unfortunately, and it is difficult to model thermal coupling. Let's say you have 2 fingers heating up, or 5 fingers in a transistor heating up. They have a temperature distribution that is not symmetrical, and you need to take that into account because one finger will hog all the current at the end. Then you need to have a thermal coupling between the fingers, and you need to pull this node out. And then you have to add the thermal resistance of the device itself here and the coupling thermal resistance multiplied with the power of the adjacent device. This slide just shows, or gives you an idea about the numbers, let's say the values of a thermal resistance for a typical silicon germanium process. I'm going to skip most of it. And please correct, this unit should read Kelvin per watt. It's just, it just got flipped. So let's move from electrothermal effects to lines at high frequencies. We have very different structures when we look at lines here. The right-hand figure shows what we usually expect when we talk about lines at high frequencies. There's a single or double line on an insulator and a lossy substrate. On the right-hand side, there's something that turns out to be quite different animal, sort of. This is the layout of a multi-finger transistor with the emitter stripes here and the base stripe here. And if we draw a cross-section, then we will see that we have possibly a silicide, a highly doped polysilicon, then a p-n junction, and then an extremely lossy base region, which is, of course, highly doped to reduce the base resistance. And the modes of operation in this structure and in this structure can be very different, and so the modeling is not as easy as you might think. Again, step back and see what we can do in order to model lines at high frequencies, we can start again with the Maxwell equations, but in this case, because of the lossy substrate, we have to add the semiconductor equations, transport and material equations, and perform what's called a full wave analysis. This is very computationally expensive, and you can't use it in a circuit simulator or in a circuit design cycle. But nevertheless, numerical solutions can be performed by various methods, and what people do is for special structures and then put them in a library, the results is fit compact lumped representations to solutions to special configurations or structures, and then come up at the end with a network consisting of C, so capacitance, resistance, inductance, and conductance. In many cases, we can perform simplifications. For instance, we can model just the quasi-TEM case. This can be mapped into the well-known telegraph equations, and they can be represented right away as a CRLG network. And there are even, in some cases, more simplifications, such as electrostatic or magnetostatic case, that either give us CR or LR cases. In terms of lumped elements. I want to skip this transparency, and you can flip back and forth, but I can't on the computer. So what the previous transparency had were the frequency limits in terms of analytical equations for the various modes of operation that are drawn here as lines for a variety of cases of oxide thickness, so isolator thickness, and substrate thickness. And what the figure shows are the various modes of operation of waves on those lines. There's a skin effect mode, there is a quasi-TM mode, and a slow wave mode. And as I said, the lines are for the various cases, but the interesting point is if you look at the operating frequency of typical bi-CMOS circuits, maybe bipolar more up here and CMOS more down here, but in general, we see that we operate basically, or we have propagation modes sort of in a land of nowhere in the transition region, where we have to consider everything and cannot make a clear decision how the equivalent circuit is supposed to look and how we have to model this. Looking at lines at high frequencies, what we can do is, when we want to construct an equivalent circuit, is we can represent a line by a pi equivalent circuit with frequency-dependent elements, conductances here and impedance. And there is a lumped solution, basically, a closed form solution, and terminating that after the first frequency term gives us a representation which we can put into a compact model that is shown here, and that represents the TM case, where we have frequency-independent elements, an inductor and a resistor, in series, and then we have a parallel network. This is again the pi equivalent circuit for a short line. What is a short line? The mathematical condition is shown here, but in practice, if you look at the literature, people usually say, okay, if my wavelengths, or let's say if my line length is a quarter of the wavelengths, then I have to add more sections like these to represent the frequency dependence of the line properly. And in general, you would actually probably more go to a tenth of the wavelength in order to do that more accurately. If we have a line running over a lossy substrate, we would have to add more elements. This is a typical substrate network, as you can see it here, and with the two elements, a conductance and a capacitance. And depending on the substrate resistivity, as I said before, and I mentioned before, you can sometimes neglect one or the other element. Usually the resistor is always there unless you have SY. This just shows a bunch of structures and is supposed to visualize the various different capacitances that we have to model by lumped forms, by equations as a function of geometry of these conductors, the oxide thickness, and also, of course, a function of resistivity of substrate if there are series resistances. But I want to just talk about parasitic capacitances. And there are capacitance solver, very fast solver for the electrostatic problem. What we are looking for compact modeling, because it has to be implemented in circuit simulators, are very fast, compact solutions for this. And the next slide shows an example for instance, a pad with a line that contains all the physical equivalent circuit elements that you have, coupling between these two metals, a fringing capacitance, the bottom capacitance of that pad, substrate network, etc. And as I said, this is an example for a very compact equation, fairly accurate equation actually, which models this fringing capacitance as a function of the geometry. And these are the type of equations that we really need for a compact model for passive devices, but also for active devices, for parasitic effects. This is basically continuing the example. That's a close-up of the transistor we have seen before. And it's just showing the metal studs. You see these metal towers here, they're fairly close together, and you can imagine that there's a lot of capacitance in between these large metals here. And I've tried to visualize this a little bit better here with the different capacitances that would have to be calculated. And then we have to add these capacitances to the typical available compact models in simulators, and especially at small transistors, or sometimes also depending on the layouts for power amplifiers, these capacitances can be very important and degrade the performance. And finally, the last slide for talking about parasitic effects, about inductances, just a little primer on inductances. The inductance itself represents the stored magnetic energy, if you recall that. So if you have a stripe here, again, a metal stripe running over insulator and substrate, you want to calculate the inductance, for instance, then this is a general equation that tells us if we know the current density distribution in that conductor, we can calculate either the self-inductance or the mutual inductance. And these two equations here are again widely used lumped forms for calculating the inductance, in this case a self-inductance, as a function of the dimensions of that line. Now we can move on to integrated passive devices, and we have the ingredients to construct models and equivalent circuits for resistors, voltage-independent caps, variable capacitors, and at the end, inductors. And we already have had enough, have enough information about the different processes and what the resistor and other passive element offerings are. This just emphasizes again that we have very different types of resistors, and two of them are shown in the next slide. On the next slide here, on the right-hand side, the classical diffused resistor, a very cheap solution in many processes, sometimes preferred to offer. And this is the solution usually designers prefer more. This is a film resistor, I would like to call it. The film could be polysilicon or another material here. And the isolation of this one, as you can see, is better because it has silicon dioxide here compared to, in this case, junction capacitance. And underneath this resistor structure, there can be a well, either an N or a P well, so it's an isolation implant or a highly doped N well. And that changes the equivalent circuit, as we see in the close-up here. But let's focus first on the resistor structure here. This is the desired resistor. These are parasitic end contact resistances. If the resistor gets long enough, we have to include at least a self-inductance to keep it as simple as possible. We might have to add more sections of the equivalent circuit on the left-hand side, but let's just look at the other elements. There is an isolation cap, then there is a junction cap down here, typical substrate network, possible resistors of the substrate contact here, and what we end up with after lumping some of the elements for onto high frequencies, we end up with this compact equivalent circuit for a resistor, where we have these two terminals as a desired terminals, but we have two more terminals, so we have 4 terminal structure, and you can imagine that it causes a little bit more effort than you usually think to characterize and model a resistor for high frequencies. The assumption for this equivalent circuit is that the wavelength is much larger than the length of the resistor, and once the length of the resistor element comes into the order of the wavelengths, we would have to just add more sections here. This is a summary of just what I explained. The elements is sort of a to-do list in order to come up with a geometry scalable resistor model, and the only issue here are, again, geometry scalable compact equations for the substrate. Let's move on to the independent capacitor. This is an overview of the various structures. It shows that we have different types, again, of voltage-independent capacitors. And it also gives a qualitative comparison of the features of these various capacitances. And again, what we need is a variety of model forms, or what is required, for instance, for a foundry, and what designers want is a variety of model forms for all these different capacitances. And two of those are shown here as the layout and the cross-section. I would like to, well, let's first talk about the polysilicon insulator silicon capacitance. There's a sandwich basically of these layers. You can imagine that there is a significant series resistance that degrades the quality factor of the capacitance compared to a construction or a structure like this. I would like to focus on the MIM structure here in the next figure that shows, again, a close-up and the equivalent circuit, the physics-based equivalent circuit. This is the capacitance that we actually want. And all the other elements are parasitics that are unavoidable. For instance, there might be some contact resistances in the metal. There are certainly isolation capacitances. There's a usual substrate network. And we end up, again, with a compact model that is a three-terminal model where we have the desired capacitance here and a whole bunch of other elements that would degrade our quality factor but need to be included. And again, what happens is that most of these capacitance structures are being laid out as finger structures. So people make them long, make this thing here long and narrow in order to reduce the resistances and increase and maximize the capacitance of the structure. And again, if the dimensions get too large compared to the wavelengths, you would have to add sections. And I can skip this again. This is just a list of the meaning of the elements that I just discussed. And this one gives you an overview on the numbers from various technology, various papers here as references, just to get an idea what the typical density in femtofarad per micrometer is, etc., for the various capacitance structure. You can go through it when you have time. And so we can move on to the voltage-dependent capacitors, also called Varactors. There is a number of devices. We already covered in the previous talk the device design issues. The classical solution is a diode, the two types of MOS Varactors, and there is even a MEMS structure. And in modeling, what happens usually is that people measure, lay them out, measure them with S parameters, fit the S parameters for a very small number of structures, and then give you a library with just a very few devices. And I tell you later why. First of all, let's take a look at the classical solution that is a pn-diode. This is a typical layout, so it shows that there's usually a finger structure with long and narrow fingers. Here's the cross-section. And the desired profile is a so-called hyper-abrupt doping profile. This is the highly doped P region, and this is the hyper-abrupt profile in the N region. And that type of profile maximizes the change of the capacitance with voltage in order to give you as much tuning range as you like, or as you want and need. But in many processes, we don't want to spend an additional implant, so we have to live with a constant doping profile. That just impacts the capacitance change with the voltage. Again, if you want to construct a compact model, then we can look at this close-up and of the structure, and these elements here are physics-based equivalent circuit elements. For instance, contact. This is the actual desired voltage-dependent capacitance. Here and here, there are bias-dependent access resistances. There's a lot of other parasitics. Partially, we already discussed those. Plus, self-inductances and series resistances in the fingers. And we end up, after lumping some of these together, with this 3-terminal equivalent circuit for a pn-diode Varactor. As you can see, these equivalent circuits for high frequencies are not as simple as you think initially, and as you can also imagine, the effort for determining all the elements and make them as a function of geometry is not that simple. That's again a list of all the various elements, plus a couple of other things on issues that might have to be included in Varactors. And this one here is again a technology overview that I have to skip to if I want to move quickly to the MOS structures. In pure CMOS processes, it is often a better choice to use MOS Varactors because they have quite a good tuning range, or can have quite a good tuning range, than the diodes that we have available in a CMOS process. This again shows a typical layout for an accumulation mode. And actually important is here the cross-section where you can see the difference between an accumulation mode and a inversion mode Varactor. Both of them are possible and to use. It is important to mention here that the MOS models that you usually get in a library cannot be used at those high frequencies. As a high-frequency model, because people usually, when they extract parameters for a MOS model, they focus on completely different operating ranges, and usually they don't model, for instance, accumulation very well in MOS models, because that's something that is not being used in regular operation for RF CMOS. So there is an additional effort for the foundry to extract parameters specifically for these Varactors. And if you look at the equivalent circuit and want to construct a physics-based equivalent circuit, then we end up with this very busy equivalent circuit here with all these parasitic resistances, overlap capacitances, series inductors, and resistances of the gate, which we can map into this equivalent circuit here. It is very important to include the series inductors here because they determine the self-resonance frequency of the Varactor and the validity limit up to which you can use it. There might be even leakage issues, so you have to include a breakdown source, current source here, and a bunch of other elements that again cost some effort to model and to characterize. That's again the list of the elements of the previous slide, and that is a technology overview of what you can achieve typically in various technologies. Now the final element here is the inductor, and I'm going to go through that only very roughly because there is a host of literature and references for inductors. People have done a lot of work in recent years to model inductors. This is just a very, very quick overview what we have. Usually we see on many chips, if you look at the ones we have seen before, we see this type of inductor layout, but there can be also circular layouts and octagons and all sorts of different geometries. And there are a bunch of parameters that are important and determine the inductance of this structure as well as the quality factor. So generally we have to model these types of various types of structures. Of course, one process usually offers only one type, but we want to in general have an inductor model that we can apply to various processes. And this just shows a cross-section of basically the structure. We have possibly a thick metal here over a fairly thick oxide. And if we take a close-up again and insert the physics-based equivalent circuit elements, we find, again, there is a series resistance and inductance in each turn that we have to consider. There are isolation capacitances, and there is the typical substrate network down here. And the most widely used compact model for Varactors is shown here that gives us the desired inductance, the unavoidable series resistance, isolation capacitances, substrate network, and a capacitance that takes into account overlap between the metal lines when we have to connect them. And the inductance and resistance become frequency dependent because of the skin effect at high frequencies, and this is a typical solution to make this equivalent circuit also valid for higher frequencies. So you can add sections this way by just adding parallel LR elements and scale them properly. That's a summary of all the elements I just discussed, and I would like to skip over this one. That's a typical or one solution that we can that we can have, and I'd like to go into and talk a little bit about characterization and validation. The first thing is de-embedding. If we measure a device, sometimes tiny devices compared to the parasitics, then we need to get the actual characteristics of the device under test. I show you an example of the impact of various de-embedding schemes on the Y parameters of a bipolar transistor. There is a bunch of bipolar transistor results and MOS transistor results. I'm probably going to skip some of them, but it depends on how we do in time. So let's talk about de-embedding first. What you see here is a typical what we call RF or high frequency pad, test pad and test layout, where we have a device under test sitting here. We have signal pads on both sides, which are connected with lines to the device, and there are many different types of layouts. This is just a schematic example here, and there is the ground pads on both sides. So this is a ground signal, ground configuration. From what we have learned before, we can represent the signal pad here by a lumped equivalent circuit, for instance, like this, and we can represent the lines at high frequencies by a lumped equivalent circuit like this, for instance, which we will need in order to de-embed the actual characteristics of this device from all these parasitics that are sitting around it. And on top of that, when we have this on the wafer and we probe this directly on the wafer, we have usually contact resistances from the probes to the metal of these pads. We have underneath the pads, again, there is an oxide, there's an isolation, and there's a substrate coupling network also between the substrate coupling between the signal pads and the ground at high frequencies. Usually you might think that, well, why don't we move just the pads into the highest metal layer? That is something that you can really do if you have to, and you have to do, let's say, if you're measuring at, let's say, 100, we want to measure up to 100 gigahertz. But in many cases, you want to pull out the wafers early. You don't want to go through all the metallization steps in the fab and wait another 4 weeks until you get the devices out. So in many times, people put the metallization into metal layer 1 or 2, and then you have to cope with all these parasitics much more seriously than if you pull it up to a higher metal layer. How does de-embedding work? What people usually do is they surround the device under test by an equivalent circuit that looks like this. It has parallel conductances. It has series impedances. They can be represented by more complex elements than just a simple, for instance, series resistance or a capacitance. And then there are a couple of test structures additional to the structure with the device under test. There is, for instance, an open structure, there is a short structure, and the open structure, you can easily imagine, if you measure this one, it gives you most of the, for not too high frequencies, actually it gives you these parasitic capacitances that we have between the different terminals. That is called one-step de-embedding. If we just strip off or determine the conductances here, and we strip them off of this equivalent circuit or of the characteristics mathematically of the Y parameters that we have measured for the whole equivalent circuit, then we are left with the series elements, and if we also measure an open, for instance, we can determine the series elements and we can also mathematically subtract them. This is the typical way, and there can be actually 3- and 4-step de-embeddings, so we can determine more sophisticated equivalent circuits for all these parasitic elements and have a more accurate de-embedding procedure. And the impact of the various steps of de-embedding on Y parameters, these are the 4 Y parameters of the transistor from Y11 to Y22, real part, what we have now, this is magnitude and phase, and the de-embedding schemes are labeled with 1, 2, and 3 for a 1, 2-step, and 3-step de-embedding, and you can see that there can be significant differences between the measurements, which are represented by the symbols here, between the measurements and the final result obtained by a 3-step de-embedding, where we have got rid of all the parasitics in the original structure. When we talk about model validation, of course, when we deliver models to designers so that they can start using them for their purposes, then they usually want to see comparisons between devices, measurements on the wafer, and the models. And of course, when we look at high frequencies, one important quantity is the transit frequency. And as mentioned today in talks before, this is not the most important quantity, but it is a most, I would say, for high frequency processes or applications, was one of the most widely used figures of merit that people also use to characterize their processes in terms of speed. This equation here shows a form of determining the transit frequency. Is a very compact equation. You just need a single or spot frequency measurement to actually do this. You don't have to go and find a 20 dB per decade slope. This works in principle to almost zero frequency, but you cannot measure at those low frequencies the imaginary part, which is the phase of the Y parameters. So usually it's fine above the 3 dB or at the 3 dB corner frequency of FT. The figure here shows you for an advanced compact model the transit frequency versus, this is a bi-CMOS process, production process, versus the collector current density. The symbols are the measurements, and the lines is the model representation, and the curves are valid for different VCE. So the highest VCE gives us the highest FT, and the low VCE, this is 300 millivolts VCE. That's pretty low. That's something that you will hit in a power amplifier, for instance, when you run into saturation. And you can see that the compact model, that advanced compact models can capture this low voltage still pretty well. Another figure of merit that was mentioned today is Fmax, and Fmax usually gets extracted from the power gain. There are various power gains that we could extract Fmax, and but my opinion is that because that difficulty actually to find minus 20 dB per decade slopes in an Fmax measurement, Fmax is not really a very good number. Everybody can sort of do a lot of I would sometimes fake to get a high Fmax. You can take points at some place and get whatever Fmax you want. What I rather would like to look at is the power gain, in this case the unilateral power gain, and as I said, there are many more power gains, and compare the power gain, for instance, at a given frequency as a function of current density. And you see here the symbols are measurements, and again the solid lines are an advanced compact model, and you see that you can actually achieve a very good agreement for the power gain, and this is much more valuable than quoting a single number, Fmax, or even running Fmax over current density. When we talk about model validation, it is very useful that designers see the model also applied in a circuit. Sometimes they don't believe all these single device comparisons, and they would like to see, so how does it perform in a circuit? This is a Bluetooth application, actually an LNA, where we see a bunch of curves. First of all, the power gain of the device, then we see the fundamental output power versus current density here. Actually, in this case, it's the input power. It's easier to read from here. This is the output power versus input power, and you can also plot this over current density to see the dips in the various harmonics. And this is a second harmonic and a third harmonic. Symbols are measurements, and the dash lines or the lines in general are simulation results with an advanced compact model. And the interesting thing is that the simulators, these are two different well-known simulators, differ at low power levels significantly, as you can see here. This is something I would really like to point out, that designers have to be aware of the fact that the simulators can give you problems when you compare. It's not always the model. Don't always blame the model and say, oh, the models are bad. Just look sometimes at your simulator, and you will find that also the simulators don't give you the right results or the same results. That is actually a serious issue still for some of these high-frequency simulators and simulations. That's from the same Bluetooth product, that's a power amplifier. Again, the power gain here, the output power versus input power is this one for the fundamental, and the blue line is the power added efficiency. Symbols are measurements, and lines are a compact model. And as you can see, again, there's a pretty good agreement, so you can actually do some design, although this is really not driving a power amplifier to the limits as in some other applications. But you can, for those things here, you can already get a pretty good agreement between CAD methods and experiments. I'd like to skip the next two slides because of a time constraint and move on to trends and issues in compact modeling. Let me try to explain this transparency here a little bit better. Obviously, in high-frequency applications, we're moving to higher frequencies. You want to put more information into the same channel or just transmit more information. And this causes or is also the basically consequence of a reduction of structure sizes. And on the other hand, if we increase frequencies, then we get a much larger relative impact of parasitics, as we have seen, for instance, the substrate coupling. It is unavoidable, and it becomes more and more important at high frequencies. Now, when we look at this in terms of compact modeling, then we're wondering, of course, if we get 20 nanometer base widths in a bipolar transistor or 60 nanometer MOS transistors, we're wondering whether our present compact models and the model formulations, which all rely, or most of them rely on drift diffusion. There's just very few models, maybe exploratory models, that use a wider scope in their equations. Whether drift diffusion, for instance, is still correct. But what we usually do is we use simulators to construct compact models, to understand the device, use the simulation results, figure out what simplifications we can make in general, and then come up with a new compact model equation. But what we are missing really are some user-friendly transport solvers where we can figure out, do we have to take into account high energy effects in those devices, or are they just still irrelevant? And so we can use those simulators. And on the other side, because of the high frequency effects, we will have to move and use some electromagnetic or Maxwell solvers. There is no way around, especially for passive devices, where parasitics play an even more significant role. And only when we have these things properly together, we can construct new compact models. Another hot discussion and something that users or customers request from foundries is the capability of doing statistical and predictive design. And the goal of the first one is to investigate and actually predict the impact of process variations on circuit performance prior to fabrication or to tape out. And the purpose of the second one, predictive design, is actually provide designers with model parameters or models well in advance of process qualification. Let's say a year before the process gets qualified, they want to start their design. And the problem is that the usual cycles that we have, especially for statistical modeling, where we use, let's say, process simulators, device simulators, they don't really meet the time constraints in industry. And the requirements here in order to do statistical design is really that we have physics-based, geometry scalable compact models available so that we can run circuit simulation and include process variations within those models rather than having to go through complicated numerical simulations. And the additional benefits by using those types of compact models are that we have a higher degree of freedom from a design point of view. We can do optimization. Design is a lot about sizing the transistors properly, choosing the right width and length and aspect ratio. for the devices, and we can do this with scalable models very easily. We can actually move on also to, in the long run, do some automated optimization, circuit optimization. There are attempts doing this in CMOS, but in high-frequency applications, there's still very little. And scalable models also provide a basis for simulation of matching. This is related to the previous slide. Concurrent engineering is related to predictive modeling. When we want to predict model parameters very early, the conventional approach is going through all these hierarchy levels of simulation, and there are two critical time-consuming tasks. One is process simulation, and one is fitting compact models. And usually those models are being fit by sort of some push-button tools, and what comes out is very often not very useful. And it takes a lot of time to do this, especially the process simulation. The suggestion and proposal is actually to go take process information, which is always available in advance from process developers. Also take some device simulation, selected results, merge and put this properly together with a tool that can generate physics-based geometry scalable models. Generate those parameters, and all this can be done in a very short time frame, and it actually, you can feed in sheet resistances, you can feed in capacitances per area, which is directly related actually to design, and you know that very early on in the process. While on the other hand, you would have to twist the process simulation and the parameters until you get something useful in terms of sheet resistances and other parameters. There's a lot to say about compact model development. It is a long story. It takes a long time to do this. And I see you've been standing here, so I'm going to skip this transparency and just and say a few words about the model complexity. What you see here is a chart, number of model parameters versus time for a bunch of MOS models and a bunch of bipolar models. You see that we get more and more complex compact models in terms of parameters. That is obvious. We include more and more physical effects for which we need parameters. That is fine, but you have to be very careful, discarding models with a larger number of parameters, just comparing, let's say, a model of 110 to 70 parameters or something. You have to look very seriously what effects are modeled and whether the parameters can be extracted with a reasonable effort. If a model has more parameters, but you can extract the model parameters easily, that is still a model that is preferable. And that brings me to the summary of this talk. There's a couple of statements I would like to make here. First of all, compact modeling should be driven by process development. We have a continuous improvement of processes and bringing continuously new effects in. And it should be driven by circuit design, because these are our users and customers. Model development does not come for free. Some managers in industry think that sometimes. You just have some university guys, lining out a model on a napkin. That doesn't work. It takes a long time to put things together for a compact model, and especially a production compact model. There is a lack of good model forms. And one of the most serious bottlenecks is that we can't get the model in a reasonable amount of time into a simulator. The simulator interfaces are just terribly inefficient, and we need to move on to model compilers. And there is new work on model compilers, so we get the same model formulation into all the simulators. That's very important, and that obviates the attempts of some people to do a model standardization, which I think is as bad a solution as if you would standardize LNAs or you would standardize processes or simulators. A note to the foundries is don't underestimate model parameter extraction. There is no push button tool for model parameters. You can't have monkeys pushing buttons on those tools. You really need engineers with brains doing a model parameter extraction and find out what's wrong in their measurements or designs. And finally, go back to the cost of the increasing and exploding mass cost. I think that provides a lot of motivation to put more emphasis on CAD tools and compact models. Thank you.